guys. Thank you for joining us from the floor again.
Sure. All right. Hi, everyone. I'll let you introduce yourself, Dr. Zhu.
Okay. My name is Feng Zhu. Currently, I'm Associate Research Professor at Hopkins Extreme Material Institute, which is a division of John Hopkins University. I joined my current institute in early 2020. Before that, I worked at Wayne State University in Detroit, Michigan, and then Embry-Riddle Aeronautical University in Daytona Beach, Florida. My work is mainly focused on extreme mechanics, which is consistent with the name of our institute. I study the material behavior and structure response and extreme loading conditions like high-speed impact, ballistic penetration, high pressure, and blast loading. Likewise, I'm interested in the human body response and the injury and similar condition. For example, the car crash accidents, contact sports, and some military environment. So I try to combine these two areas together and then develop high-performance safety products to reduce the injury risk. And in the design process, I emphasize to use the AI or data-driven methods like machine learning. So basically, I'm working on three areas simultaneously: structure mechanics, injury biomechanics, and engineering design.
Okay, great. And he's from Johns Hopkins University. So, so you have a connection between your research and automotive engineering, and it's a big overlay. Can you talk about that a little bit?
Okay, my work on extreme mechanics is directly related to passive safety of vehicle system. We know that the safety of transportation system, it can be classified as active and passive safety technology. Active safety features, they try to avoid the accident before they happen by using computer sensors and control system. For example, lane keeping, collision warning, something like that. Passive safety features, on the other hand, take effect when the accident cannot be avoided. For example, sometimes your car may be hit by another vehicle that loses control. That may happen. In that case, the passive safety technology must be able to dissipate the crash energy quickly and reduce the injury risk. My work, as I just mentioned in the last question, I'm working on structure mechanics, injury biomechanics, and design. In the first area, my work mainly focuses on lightweight energy absorber on the vehicle, single structure, cellular solids with either random or periodical microstructures, like foams, honeycombs, 3D printed lattice material, something like that. They can be used on the vehicle to dissipate the crash energy through large deformation. So I studied their behavior and the dynamic impact loading condition. For biomechanics, I have been studying the occupant injury response in the traffic accidents. I use numerical model, human body model to simulate the car crash accident and then analyze the injury. In the design area, I develop safety products for the transportation system, like crash-worthy vehicle structure and the restraint system, and safer energy storage system, like the lithium battery used on the current electric vehicle. I can show you some examples.
Okay, yeah, that's great. So I heard honeycomb, I heard additive manufacturing. So all of those structures can kind of come together to protect the car in the end.
Right.
And yeah, some AI and your lithium battery structures. I'm really excited to hear about that. Overall, what would you say the trends in passive safety have been? Like if you kind of look back and kind of see where it's headed, how would you kind of look at that as a whole? And where do you think it might be heading?
Passive safety has been subject of the vehicle safety for a long time. At first, I think the focus was placed on the just vehicle crash structure design, structure crash worthiness, and restraint system design like seatbelt. I think right now people still working on these features, however, trying to find new ways to improve them. For example, the engineers are now using lighter weight but higher performance material and structures for vehicle structure design. For example, some new alloys, advanced composites, and the lattice materials. These parts now can be easily fabricated using 3D printing. In biomechanics, right now the injury analysis can be done easily by using some computational human body models. These models have become more sophisticated by including more detailed anatomical features to improve its accuracy. Now people can simulate the traffic accidents by combining these sophisticated human body models and detailed vehicle models. And I think this is a major improvement over the use of like old version simplified model in the past. In the design area, now high performance computers and the machine learning algorithms are being used to better handle the simulation data set and speed up the design process. So looking ahead, I think passive safety technologies are being expanded to the new generation vehicles, like electric vehicles and self-driving cars. For electric vehicles, we know that battery safety has become a concern. For self-driving cars, we have to redesign the restraint system, like seatbelt and airbag, because the occupant has different posture.
Oh,
Have to lie in the
so there's a different structure in an electric vehicle. So the occupant might be sitting different.
right, may face back. Right?
Oh, they might, because, or in autonomous vehicles, it
we
might
have
be.
completely redesign the
So
restraint system.
passive safety really is going to be changing a lot
Right.
with all of
We
this.
have a lot of work to do in the future.
Interesting, very interesting. Okay. All right. So kind of following up with that, can you give us an example of a research project that you can solve the current challenges in passive safety?
Okay, I'm happy to show the audience our recent work related to the lithium vehicle battery system safety and some use conditions. So this is my slide.
Yeah. You're going to say next, and
Okay.
Shane will take it over.
Next,
There you go.
okay, we start with some background information. Why do we study the vehicle battery safety? We know that the electric vehicles or hybrid vehicles, they have a big battery system. If there's a crash accident, the impact force energy can transfer into the battery very quickly in milliseconds, causing structure failure, short circuit, even fire and explosion. We have seen many cases from the news media reports. Here on the slide, I'm showing two typical examples. However, the studies in this very important area are still very limited. Next. So our work is mainly to better understand the vehicle battery system damage behavior and the crash loading conditions at the multiple levels, from battery cell to the entire electric vehicle. We try to develop high fidelity numerical model to simulate the crash accidents, and then develop better safety countermeasures for the battery module on the vehicle and electric vehicle. Next page. Okay, so here we can see some typical battery cells currently used on the electric vehicle, including the cylindrical cells, the prismatic cell with a hard casing structure, and the pouch cell with a soft casing. So our work mainly focus on the second and third type because they are more widely used on the current electric vehicle. Next page. This is a typical example. It's a prismatic battery system. Left-hand side, the picture shows the battery module. If we decompose the module, we can see the major components on the right-hand side. And 5 or 6 prismatic cells are connected to one another. The enclosure is made from aluminum. If we open the enclosure, we can see 4 layers jelly roll at the corner in stack. So this is a configuration of the battery system. Next. Okay, so we did a physical test and numerical simulation. In the following order, we started with the component level, jelly roll components like cathode, anode, and separator. Then we move on to the entire jelly roll layer, and then the entire battery cell and battery module. So we from smaller things to the bigger things. Next page. All right, so at the component level, we did the standard material coupon test, like tension, compression, on each individual component of the jelly roll. Anode, we can see anode, cathode, separator, and enclosure. And then we develop numerical model to simulate this test and calibrate the material loss in the numerical model. Next page. All right, we did a indentation test on the entire jelly roll layer using this steel wedge. This material shows strong orientation effect. If we cut the jelly roll in so-called winding direction or 0 degree direction, the material is pretty weak. So we can see a crack through the thickness, inclined crack. However, if the material is cut in the 90 degree direction, the behavior is much stronger. We don't see any crack or failure. So that indicates this jelly roll material is a highly anisotropic material with orientation effect. So when we develop the numerical model, we have to consider this effect carefully. Next page. All right, so this is indentation test on the jelly roll layer with enclosure. So during we use a steel punch and the same wedge for the jelly roll material. And during the test, we measure the voltage change in addition to the force. So we can see the results here. In the two plots, the black color curves, they are force response, and black color curves, they are voltage response. So we can see the voltage, it dropped to 0 quickly, right? So that indicates the short circuit of the battery and the complete failure of the battery cell. Next page.
That's a good thing. Okay.
That's bad thing.
That's a bad thing.
totally, it's complete failure. We developed the numerical model to simulate this test. So here we can see the simulation of hemispherical punch loading. We see a good agreement between the test and the simulation. Next page. So this is simulation of the wedge cutting test on the jelly roll material only, and right-hand side is the entire battery cell with enclosure. Again, we can see a reasonable agreement. Next page. Okay, so this is the impact test on the jelly roll material and the battery cell. This condition is closer to the actual crush condition. So we use the job tower to run the test. So we can see the battery cell inside the test chamber. The impact velocity was up to 7.5 meter per second. Again, we measure the voltage in addition to the force during test. So the picture shows the impact test on the jelly roll material and the battery cell. Next page. Okay, this is module level. We use this big steel wedge to cut the entire battery module in different direction, and then use numerical model to simulate this test. So here we can see the top loading condition and side loading condition. Next page. All right, so that's the first case study, prismatic battery. This is second case study. It's a pouch cell without a hard casing structure. The picture, it shows the configuration of the battery module. On the top, we can see a cover plate. It's a very strong structure. The next step, we are going to optimize this structure using some data-driven method, and then cooling plate, cushion, and the pouch cell. So this is a configuration of this particular battery system. Next page. All right, we did a similar study on this battery from the component level to the module level. So here I directly jump to the module level. Here we can see the testing and simulation of the wedge cutting. We use the same wedge to cut the battery module, so we can see the failure mode. Next page. This is punch loading condition. Same thing. We run the simulation to simulate the physical test. Next page. Okay, so after the testing and modeling work, we expanded this study to design, how to better design the battery module structure and make it safer. Our test results show that the cover plate, as just mentioned earlier, it has a significant protective effect without any fracture even under the wedge cutting. So our design improvement was focused on this structure. The original design of this cover plate is a monolithic corrugated plate, and in the new design, it was modified to a sandwich plate with multiple layers, but with the same mass, in order to increase the peak force and displacement at the beginning of the short circuit. So here, left-hand side, we can see the original design of the cover plate. Right-hand side is new design, 3 layers with 2 phase sheets and lattice coat in between. Lattice material, we know is a very good energy absorber. The new design has the same weight with the old design for comparison purpose. Next page. All right, so here we want to use machine learning algorithm to optimize this new sandwich cover plate to improve its crash worthiness performance. Basically, we need to do 3 things. Number 1, we want to mine the simulation data set, then discover some hidden complicated relationship between the design objective and the design variables. And then we want to derive some decision-making rules to quickly generate a new design case with desired performance. Next page. The design process has 3 main steps. First step, key parameters determination, then data set generation, and then last step is application machine learning for the optimal design. Next page. Okay, now I would like to show you a very simple example to demonstrate how this method works. We start with the first step, key parameters determination. We assume that the battery module is loaded by a cylinder from top, and the 4 input parameters or design variables selected, including the phase sheet thickness, coat density, diameter of indenture, and impact velocity. The output parameter or response is energy absorption. We want to increase the energy absorption. It should be noted that this selection is totally arbitrary. It can be changed based on specific design objectives or preference designers. And based on the values of these input or design variables, we can totally generate the 54 combinations. Next page. All right, so each combination here is called a DOE, design of experiment. Then we run the numerical simulation for each individual DOE and calculate the energy absorption. And the simulation data set, we form a simulation results from a data set like this table for the subsequent machine learning model training. So this is a second step, data set generation. Next page. All right, so third step is application machine learning. Here we use a algorithm is called a decision tree. Decision tree is a tree-like graph to link the input and the output parameter. A typical decision tree, it has a root node on the top, several leaf nodes at the bottom, and a few internal nodes in between. The root node and the internal nodes, they represent design variables or input. The leaf nodes, they are label of performance, design performance or output. And the path from the root node to one of the leaf nodes is a decision-making rule to link the input and output. Here we can see a very simple but widely used example to show the principle of this method. It's regarding credit card application decision by the bank. We know that every bank has a big data set for existing customer, right? They use this big data set to train the machine learning model, like a decision tree, and make a quick prediction for the new applicant or new customer. For example, in this is a typical but highly simplified decision tree. We can see the root node and the internal nodes, they are input, and the leaf nodes, they are output or label of performance. So given the information of a new applicant, we check the top, the root node first. So the root node is salary. If the salary is lower than 100K, then we go to left. Check the second node. If profession is teacher, then we go to left. Good credit, that means approval. Otherwise, we go to right. Bad credit, that means application will be denied. So we can see that using this kind of a decision tree, based on the knowledge of existing customer, we can make a quick decision for the new customer, right? We can use the same idea to design the structure. I'll show you how. Next page. This is theory. I skipped this part. Next page. All right. So we want to use decision tree to quickly design a cover plate for the battery module. The first thing we need to do is to classify or label the design performance. So in our data set, we assume that the 1/3 highest energy absorption value cases, they labeled as good designs, or G, and 1/3 of lowest energy absorption value cases labeled as poor designs, or P, and the others in the middle, they labeled as intermediate designs, or M. So based on this labeling strategy, we can generate a decision tree like this. Again, the root node and internal nodes, they are design variables or input, and the leaf nodes, they are output of performance. So each path is a decision-making rule with corresponding performance, right? So for example, if we follow the branch B7 in that green color circle, we can quickly generate a new design case with good design performance without the need of running additional expensive numerical simulation. So this is the power of machine learning in the structured design. Next page. All right, the typical good design, typical poor design predicted by the decision tree. Next page. All right, this is a brief summary of this work. So we developed a simple solution to achieve the rapid design of the protective structure and some other goals. There are many machine learning models available. However, they are not able to achieve all the above goals at the same time. And this decision tree method, it can be applied to many different systems with multiple parameters. I can show you some other examples. Time now. Thank you.
Oh, that's very interesting. Yeah, let me get back to my questions. Yeah, so when you're looking at this AI or machine learning algorithms, and you said that there's many other AI, potential for AI.
Yeah.
Do you have methods in injury analysis that you would like to talk about a little bit?
Okay. Yeah, I'm happy to show you another example. That's an application of this method in biomechanics.
Yeah.
So can you show the others?
Should go on to the next one. Nope. I don't know if we have the other one. I guess maybe we can talk about it. So in the same way that you're using a decision tree here, so you're kind of incorporating more physics aspects. So you have like a more like finite element analysis of the body.
Yeah.
And then so in the similar vein that you use a decision tree here for like the structural analysis, what did you do to incorporate the biomechanics and the physical elements?
Another example I would like to talk about here is regarding the head injury risk analysis on the e-bike cyclists. Due to the current sharing economy, the e-bikes are very popular in the big cities. However, that kind of e-bikes, they much faster than the ordinary bike and very quiet. So they're very easy to get hit by a moving vehicle. So it's important for us to better understand the head injury risk of the e-bike cyclists. So in that project, we want to use the same method decision tree to quickly evaluate the injury risk of the e-bike cyclist without running additional numerical simulation. Basically, the ideal procedure is similar. We want to develop a decision tree based on the simulation data set. We start with some like input parameter. We cannot call them design variables. We can call them influential factors, like the relative velocity between the moving car and the e-bike, the impact velocity, impact angle, the body size of the cyclist. So these are input parameter. And then we run the numerical simulation for each individual case to generate a big data set, similar to this battery study.
Right.
Then we use apply the machine learning to develop a decision tree. Again, the top node, internal nodes, they are influential factors. And the leaf nodes, they are head injury risk level, like a high level, middle level, and the low level. So based on that decision tree, we can quickly, given the information of a new case, we can quickly generate a path and then make a decision, make a prediction for the injury risk without running additional numerical simulation.
So with those input characteristics, you can actually, help design the vehicle based on what type of injury would happen with these parameters. Right. Would this also influence would this go into like, into when they see the doctor and like, this is gonna, hey, I don't know what's happening. You could actually provide that information. Like, this is what we expected to happen based on our, is that how
it's like a tool of diagnosis.
Yeah, so it can help on both sides. Like,
applications.
Yeah, that's very interesting. And then it enables you how to design the vehicle. How would you change the vehicle based on some of these things that you're finding with that combination multiphysics with biomechanics? How would you change a vehicle based on that?
Vehicle, I see it's a more complicated structure. It's a multiple level, system level, component level. For each individual component, we have a number of geometry parameters. So basically, we can follow the same procedure, but we use multiple decision tree. Actually, I have a project directly related to this. So we decompose the whole vehicle with several systems, and each system we divide it into several subsystems, and then component level and geometry feature level. So for each level, we use a decision tree to make a quick design. So it's a top-down design process. Save a lot of time.
Save a lot of time. I can definitely save a lot of resources, computational resources. I see what you're going with. That's really great. And it's very interesting, especially for the lithium batteries and the fires that can happen because, in those crashes. I guess one last question I wanted to ask is, about your experience with publishing your research in tech papers here at WCX, also getting accepted into the proceedings journal that we still have, which is kind of what our peer reviewers thought would be a paper that is worthy to go into the proceedings journal that we still have one of. So if you could talk a little bit about your experience for other authors or anyone else in the audience.
I have been actually actively involved in publishing with SAE, organizing sessions for many years, over 10 years. I think it's very important for the researchers in all areas related to automotive engineering publish their findings through SAE. SAE publications not only serve as a platform for researchers to communicate their research work to a broader audience, but also provide some very valuable insights and knowledge to the industry professionals and policymakers. Through my own experience publishing with SAE, I have been able to share my ideas, research work to more people, receive feedback from experts in my fields, and then stay informed regarding the most recent research trends, technologies. Publishing with SAE also helped me establish my credibility as a researcher and to open up many new opportunities for collaboration and networking. So overall, this experience has been invaluable for me for the advanced research work.
Well, that's great. Well, thank you so much for sharing.